Alright, so we're going to kind of look at some operations with radicals right now. I have 4 examples to go through. One's addition, one's subtraction, and 2 are multiplication. Division we'll look at in a different video just because it's kind of got some uniqueness to it. So I have these perfect squares set to the side because the majority of time you can use these perfect squares to guide you. Now, I did a prior video with prime factorization, but it's a little longer process, and if you learn this technique, you can really save yourself some time. So I look at my perfect squares, and which is the greatest number that is a factor of 80. That's one of these highlighted numbers. Well, 16 goes into 80, right? And if you watched my last video or any other video somewhere online, you should remember that when you factor the radical, it gets both the radical symbol should be with both the factors, right? But now that I notice that this is a prime number and this is a perfect square, and I know the square root of 16, if I go ahead and kind of go back to my perfect squares, I know the square root of 16 is just one of those numbers. So I know now I have 4 times 4 times the square root of 5, or 16 square roots of 5. And then I'll put this plus sign because this is kind of here. I'll put this plus sign, this is kind of here. And I'm going to do the same thing over here. I'm going to factor this. And I know 25 is a very easy number to see that goes into this. And then times 5, right? So what's the square root of 25? Well, we can kind of, if we know these things, it's very easy. But if we don't, we can kind of problem solve them to figure it out by working through prime factorization or building ourselves a repertoire of understanding these perfect squares. So I end up with this 5 square roots of 5. So I'm just going to put it down here. Now, notice I have the square root of 5 here as a base, and the square root of 5, I guess not really a base, but part of the term. These are the radicals that are that make these things like terms. It's just like if I tell you I want to add x plus x, right? These are like terms, so I would add them together. I get 1 plus 1 gives me the total number of x's, right? So these are coefficients. So you can imagine that like the 16 and the 5 are like coefficients on variables. As long as these radical values are the same, right? I guess they call them the radicands, the numbers underneath the radical symbol. You could just add these two numbers together, and what do I get? I get 21 square roots of 5. Your calculator will tell you exactly what that number is if you wanted to find it out, but you know that's more. This is more about the idea of, say, simplifying the radicals with addition. So we need to define perfect square factors, and it's really the kind of the fastest way. Now, prime factorization is also useful, but it will get you to the same answer. This is just kind of faster. So we're going to break this up. A perfect square, pretty obvious, I hope. 100 and times what? 2. And then I have this 3 here. And of course, the square root of 100 is 10. So I'm just working out this first term in this expression, and I end up with 30 times the square root of 2. So now let's factor this one. What is a perfect square factor? This goes into 76, 36, and then times the square root of 2. Notice I do leave the square root symbols until I don't need them, because then, so I'm just going to put a minus sign here and just remind myself. But then it keeps it neater in organization, and it doesn't allow the mistakes that sometimes you might make with these square root symbols. But this is 6 times the square root of 2. Okay, the square root of 36 is 6. I just bring down that, and then I just put that here. And now, again, we added the coefficients if the bases are the same. So here, we'll just subtract the coefficients if the bases are the same, and we just get 24 square roots of 2. So 30 minus 6 is 24. So not super complicated, but there are some prerequisite knowledge that you need, which is understanding how to factor. And then we got 2 more problems. These are multiplication, so they're not so bad. They're going to follow a lot of the similar processes in terms of factoring, right? But do I have to factor them? Sure, let's just factor them for the sake. You could multiply 50 times 18 and then kind of work it out. But what if we say, I know that this is the square root of 25 times the square root of 2, and I know that this is the square root of 9 times the square root of 2, right? Because I know perfect squares. Well, now I know that this is 5 times the square root of 2, and I know that this is 3 times the square root of 2, right? These become our perfect square factors. And now, just like up here, where we added the coefficients, we can group those, and we will group the 2 numbers in front, right? So we'll group them and multiply them. These are like, if we are multiplying variables, we would multiply the coefficients. So what do we end up doing? We also have the square root of 2 times the square root of 2, and we can, I'm going to just kind of go a little bit longer in terms of the procedure. I guess I should have just made that 15, but just so you get a deeper understanding is, this is, if there's two separates, I can just put them underneath the same one, and that will give me the square root of 4, which is 15 times 2. So it's a long ways around to get to 30. And so how could I have done that a little bit faster? Well, 50 times 18, if I just multiply those two numbers, does give me the square root of 900, which comes down to 30 anyway. But this procedure is so useful that I wanted you to see it, because so many of us will skip this and then we don't really know this idea. So let's look at this one now. If we kind of go, we're at the second stage here, so let's just multiply the coefficients. We can kind of think of them that way. And then 7 times 6 underneath the radical symbol. So this is 6 times the square root of 42. And we're finished, except for one thing. And we have to kind of think about, is there a perfect square factor that goes in there? And so just always go to half that number, because your factor would be below half. So I go to 2016, right? And 9 doesn't go in, 16 doesn't go in. It goes into 48, and this goes into 45. But 4 goes in. 4 goes in. How many times is 4 times what? No, 4 does not go in. 4 does not go in. So we are, in fact, actually finished. There is no more to do. I tried finding one. Nothing worked. 4 goes into 40, so it can't go into 42. So this is our simplest form. So hopefully that helps. If you are trying to simplify them, look for more. I will release more.